Okay, so let's start today and what I will talk about today. Maybe first I will clarify something about this algebra and correlation functions and so on. And second, what I will talk today, construction of separate algebra, which are generalized this, and using something like using construction or wide model constructions, so on, and what precisely I mean, I'll explain. But let me first say a few words about what was there. And yesterday I defined Clifford's algebra. And this Clifford's algebra generated by psi I in third J star. I J belongs to Z. And I recall that all elements are skew commute. Only exception is psi I psi minus I star plus is 0. All other is 1, and all other skew brackets are 0. And yes, and then I consider the R. R was irreducible representation of this, and I needed this representation to calculate the correlation function and also explain this machinery of correlation functions here. Yes, and maybe it is good to say a little bit more precisely what is R. Yes, and no, I define R as some representation with highest weight vector and some part of this Clifford's algebra manipulate this highest weight vector, but probably it is good to understand that R can be realized as a so-called space of semi-easy forms, well, and by this I mean the following: if you have some, suppose you have some vector space which is finite dimensional with just basis v1, v2, and so on to n. If it is finite dimensional, then if we consider Grassmannian algebra or component of Grassmannian algebra like this, then if this space has a basis, maybe let us put H here, M, and then E1, E2, and so on, and E3, E10. Yes, and these indices are running in 1, 2, 3, and so on, and this thing is bases in this space. And if you are talking about semi-infinite forms, then it is a natural question what to do if n is infinity. And for example, not only this, in our case, we consider the space with the basis actually psi I, this we need. And here it means that we are interested in a question that now we have vector space with basis ei. Now I belongs to Z. And what we can do? We can consider, no, first of all, without problem, we can consider these things. And it just means the same story as here, but these indices now are not running from 1 to n, but they just belong to Z, and this is it. Yes, but also if we, in finite dimensional case, if we have some, for example, this space is one dimensional and this element is a generator of this one-dimensional space, and sometimes it is natural to call it a volume form or something like that. And why not to do something like that for infinite dimensional space like this? Yes, but in this case we can do, but formally or not, but at least we can write down the object like this: E0, E1, E2, and so on. Here E minus 1, here E minus 2. It is like this. This object can be understood as formal or not, but it is something like volume form on V. Yes, and well, and we can work with this. For example, at least formally, but we can consider in something like this also. In the case of in this case, it means I'm talking about lambda n minus 1 v, and in this case, basis here is what? It is, say, e1, e2, but some e3 is here, and then en, and such. It is not here, but all other things exist, and so such kind of elements are basis here, here. And here, if I want just to determine what is this, it is no elements here are labeled by Z, so I can erase something. For example, this, and it can be element of that kind. Or I can erase, for example, this. It also will be element here. And so this space has a basis labeled by Z. And if I want to put 2 here, it is possible in this expression erase 2 things. For example, this and that, and also with some elements there. And so it means at least without troubles, I can here it means what? But in finite case, so even now let me erase this also. I'm working with this, I belongs to Z, and so I can write down what? I can write down C plus V so on, and so it will be just Grassmannian algebra, and in this Grassmannian algebra bases are just monomials, and so this is it. But maybe even here we can ask the question about operators are acting here. Actually, it will be our Clifford algebra, but we have some evident operators. And one operator is which I want to determine by the same EI what it is doing. It is taking element from here, W, and send it to W times EI. So by this way, on this space, we have a collection of operators, which I denote by the same letters, which I show as Q commit, and they are acting by this way. Yes, other possibility is falling, because it is like skew polynomials in odd variables, then I can determine here the operators like this. These operators, what it is doing, it take a form here. Let us consider some example. No, it is acting like on this, like derivation, but it is odd derivation. And if I have some kind of form like this, maybe let us write something. Something like E minus 1, then E0, then E1. Yes, and suppose I want to apply to this. Then how I do it? No, because of this skew symmetric language, how I can do it? First of all, I want to derive, but the procedure is following. First, we can write down this as E0, E minus 1, E1 here, in order to put E0 in the first position. And after that, this makes derivation of this. It means that it is just erased. Derivation, it means the erasing, and so the result of the operation is like this. It will be minus E minus 1 times E1. This is the result of the derivation, and by the similar way, derivation are acting, and no, you can easily see that if we have monomial, and suppose in this monomial we have, suppose if I make up derivation like this. In this case, here we have not E2, and therefore it will be 0. Yes, and if I make up derivation like this, it will be it just kill this. And the result gives us E0 times E1. And so by this way it is acting, therefore, what we have now, we have the direct sum of this, M belongs to C, and on this space we have, not this D, but M is equal, it belongs to a non-negative number, so M can be 0, 1, 2, 3, and so on. Yes, and on this space we have the action of operators EI, just product, and we have the action of such operators, which so, and I determine the action version of this, and then if you have such things in the mind, then it is easy to see what kind of relation we have. Such operators, because they are just products, they are skew commute. These operators, because they are derivations, they are also skew commute. And it is easy to see that this plus is 0 for any I and j. Because we just arrange the derivation by this way, and it is natural to have such kind of equation. And also d over dI and dG plus also is 0 if I does not equal to g, and then d over dI plus is 1. Maybe no. How I define, I think it is correct. But maybe it is a mistake of -1, but it is such kind of relation. Then what we have? If we have this space, then such kind of algebras are acting here. Namely, operator psi I goes to operators EI, just product to EI. And operator psi I star goes to derivation in like this, in E minus I, and if we do this, as a result, we get such kind of relations. Right now it means that we have at least one representation of my Clifford delta, but it is not R. R will appear a little bit later, but before that, let me say that if I take the same vector space with the basis EI and take lambda infinity V plus lambda infinity -1 V plus so on, I explain what does it mean. That this is one-dimensional space with the basis like this. This is one-dimensional, this is infinite dimensional space where we erase one of the elements involved in sequence. There are 2, 3, and so on. Then on this space we have also the action of the same operators, because without program we can define the product of EI and derivation. No, maybe for you it is not completely evident, but if you think a little bit, it is easy. And as a result, I want to have that here we have the action of the same algebra, and what is changing? When it was C plus V plus lambda 2V plus so on, then these elements are killed by this, because the derivation of 1 is the derivation of 1 is always 0. And no, if I have this, then if I have this infinite product and write down times product to EI, it will be 0, because in this infinite product we have such EI, and then if we take one more product, it will be 0. And in this case, I construct all vectors starting with this by product to EI, And in this case, I take this volume form and apply this operator. And this operator extract from such product EI and also give us this representation. And so these two representations, in a sense, are rather symmetric, but role of psi and role of psi I are changing. But up to this, it is the same thing. Yes, but R is not this. R is this one, and if you have in mind what I said, that no, it is infinite dimensional space, so we have, in principle, we can play by many ways. That what we can do, if we want to get this, then let us write first formally the element like this. It is E1, E2, E3, and so on till infinity. So it means that I take in my space V 1/2 and consider the full volume form of 1/2. In this case, it is clear that I have these elements and I want to apply these elements. It means I can take this and write down the product to EI. So if I is negative, I get something new. If I is 0 or positive, it is 0. Or I can consider this operator and apply to this. So what does it mean? That if I apply operators which kill the negative things, meaning it is positive, then it will be 0. Or I kill something here. And so what I want to say? I can take this element and then apply this element and this element, and just I want to look what we get as the result. And as a result, I want to say, first of all, that we get R. And about the basis here, basis in this space will be the semi-infinite form. And it means what? That what possibility I have by acting to this and this to this form. I can erase several elements here, say this 2, and 4. And by acting this, I can create something. It can be -5, -6, and so on. And such kind of objects give me a basis in representation of my Clifford algebra. And this is just R. So the statement is what? In R, we have basis labeled by the following data. This data, let me call semi-infinite configurations of points in one-dimensional vectors. What does it mean? It means that in order to write down such things, I can have in mind the following combinatorial data. I write down the one-dimensional letters and numerate them by 1, 2, 3, 4, -1, -2, -3, and then put on these letters crosses. somewhere. But first of all, in infinite set of crosses, which condition? That in direction of minus infinity, after some point, no crosses. Maybe here, yes, and then no. But here, in this direction, after some point, in this case, for example, 3, we have a tail, which is going to minus, which is going to plus infinity. So this is a semi-infinite configuration. It means in this direction it is finite, and this direction it is not. And if I write down such configuration, I can write the vector from this space. It can be, for example, E3 here, E minus 1 here, and next E minus 3, and so it is infinite product in this direction. Okay, and now these are the basis, and Clifford algebra, as I said, is acting there by more or less evident way. You have a little bit accurate, but if you write down how it is acting, no problem. Highest weight vector is killing by elements which I determined yesterday, and then, now if it is so precise, then we can check here something what I said yesterday. Well, what was actually the statement here? I can write down psi t, which is the sum of psi I t minus I. Or I can write down psi t, which is the sum of psi t minus I. And then I had some conception of correlation functions. No, correlation function after that, because all is very explicit, you can calculate, but what can be the example of this? I can take some vector here, W, and suppose this vector is corresponding to some semi-infinite configuration. It may be configuration 1. Then I apply here psi to this vector. I apply maybe in this way psi z, kt, and t1, and psi star of t2. And here matrix element, it is W corresponding to some other configuration, C2. And no, and because it is so no, I said that this is a rational function in T1 and T2, and we can very easily see that this is correct. For example, no, in principle, it is not a big deal to calculate these things for arbitrary. But let me do it in some example. Let me take semi-infinite object, maybe like this. No, I can, maybe I can start with this, 3, and so on till infinity. Suppose it is this. And as this vector, I can take this thing. And so what is this? I act by this way. So it means if I want to take something non-trivial, I act by this by EI, and I is 0 or negative, and it gives me this. But after that, I act by this, and I want to return back, because I am talking about matrix element where this and this is just the same. Now I have in my vector space the basis, and so I can calculate what is this. And if it is, they are the same element, and it is this, that non-trivial element here can appear only if I take by EI, it means that I apply psi I. Following my definition. Then I want to go back, and so it is psi minus I star. And this is only the pair where I can get 1. All other pairs are 0, but in this case, this I is what? I is 0, 1, 2, and so on. And it means that in this case, this correlation function will be the sum of T1 power I, T2 power minus I probably like this. And therefore we have, no, this is, it is 1 over 1 minus T1 over T2, or I think in this case it is correct, it is T2 over T2 minus T1. Yes, so this is a result of a calculation, and so we see a pool here, which I promised to you yesterday, and precisely the same story appears if we take. No, first of all, now we can look if these two elements now are different. Then in this case, it is easy to see that the corresponding correlation function will be Laurent polynomials, because we will have only finite number of terms will be non-zero. If these two elements are equal, then as a result, we get more or less the same, very similar things, and it gives us that function with a pool. And if you analyze what is going on a little bit more carefully, you will see what I said yesterday, that in a pole of correlation of corresponding correlation function, you can see in front of some coefficient just identical operator. And here, this identical operator is here. Yes. So anyway, so we did this, and you can easily see that. No, well. No, statement here says that such kind of correlation function, it is what was yesterday. It is some polynomial in T1, T2. In principle, this polynomial depending in these two semi-infinite configurations, and we have a pool T1 minus T2 here. Yes, what other statement we had yesterday, which easily verified
in this special basis. One statement was following, that we can take psi t, psi prime. First of all, what does it mean? If I write down this, let me understand this expression by the following way. First of all, this is what? It is psi I times t minus I. If I write down this, no, it depends a little bit how I understand this derivative. And this, no, again, naively I have to differentiate this, and it gives me in t. It gives me psi I, and here I have t. Now, if I differentiate this, it gives me ti minus 1, and we have minus I here. Or we can understand, no, it's little bit more convenient not to have this shift. It means that by differentiation, to consider the operator t over dt, yes, and even to have minus here. In this case, we have, if we follow this, it's not a big difference, but just a little bit more convenient. Then, but first of all, it is I here in this case, and or better to put J here and J here. So again, so this is this, and this is this. But I want to understand what is such product. After that, what I have to do? I have to write down this as a sum. So here it will be t power some s, and here we will have coefficient. What this coefficient will be what? This coefficient will be just a sum psi I psi j times j, and here we have I plus j equal s. Now this is more or less what I wrote yesterday, and this operator is the infinite sum, and we need it if we want to have some meaning if we write this. But first of all, what this operator, let me say that this operator is well defined. It is infinite sum, and we get it by some manipulation with this. But if you look what this operator is doing, that we suppose we have some kind of semi-infinite form, something like 5, 6, 8 maybe, something like this. So what kind operator psi j, as I said, it is doing like this, and the operator psi I is doing like this, and we have coefficient j here, and then we sum up with I plus j, you see, is s. But if j is big enough, then the product of these two, this semi-infinite things, is 0. Therefore, it is typical situation that if I have such things, that naively it is, no, not naively, but really this is infinite sum. And from the first glance, this operator is not X. But in reality, if you apply it to this element, only almost all, so infinite sum, but only finite part of the sum is acting non-trivially on each fixed element. So it means that such kind of element is well defined and give us the operator acting on a space of semi-infinite form. Well, now no, anyway, the some kind of statement which I formulated yesterday. For example, if we have something like this. And here we have some element WC2, and here we have some element WC1. It was correlation function which I discussed yesterday, but now we can, because we have explicit definition of all, if we have these two things, we can calculate what is this. And you can see that it will be some rational function, yes, and this rational function actually will have a following structure. It will be some polynomial here, G1, G2, but here we have some pole. And no, this pole appear because we have pole here and pole here. Yes, and how do you think? What degree of this pole we have in this case? Have you some ideas what it can be? No, if you want to see it, how to make up a calculation, that it is possible to do what? To take this and this also just highest weight vector, just a semi-infinite form. After that, trying to calculate, the same vector you cannot take because otherwise it will be zero. But you can take two of them and then calculate what is this. And so you have such kind of product and then this. And again, you take component of number I here, and you have component of some number here, and you can see what is this. And then you can see that in this case, the pole will be T1 minus T2 squared. Well, either you can calculate or you can predict it from something, but at least it will be this. Now, let me use this construction to get more interesting. No, this is also rather interesting vertex operator, simple but interesting vertex operator algebra, where we have such kind of operators and calculate the operator products and things like that. But let me consider the following next example. And next example will be the so I want to take the algebra where I have psi 1, 1, and psi 1, 2, psi I 2, and psi j star 1, and psi j star 2. If I, first of all, if I construct Clifford algebra, this is again the object which I mentioned, and this object is what? That all elements from this, no, it means what? I have my previous construction, but I have double this and this. All elements are skew commute with some exceptions. But exceptions are here and here. So it means that psi I 1, psi minus 1 like this. It is 1, and similar story with 2. Psi j 2, and psi minus j 2. Here plus is equal 1. All other pairs are just skew commute. No, first of all, where this algebra is acting. To do this, also we can make up the similar construction of semi-infinite form. Well, so before I take my construction was following. I take EI. It was a basis in some vector space V. And what I explained, this is such kind of space. No, better to say this notation is bad, because actually what we get is the direct sum the meaning of I, maybe I explain a little bit later, but even in my construction that I have vector space V, and Grassmannian algebra is C plus D plus lambda 2V plus so on, and so we have some summation, but here it is 0, 1, 2, 3, and so on. And the other construction was this plus minus 1 V plus so on, and it is also summation. Here I am going to 0 up, here I am going to infinity down, but here I have something in the middle, and I can go up and down, and so our sum is this. Anyway, here is the space EI, and it is natural to think that this space EI is just basis in Laurent polynomials like this. no, and yes, and it is natural. So it means I take functions all around polynomials. This is infinite dimensional space, and they're considering the semi-infinite exterior power. But if I want to have more complicated things, I'm doing more similar story, but here I have C2. C2 is because we have here 1 and 2, and considering the semi-infinite things, maybe plus I here also. And so it gives me the basis in a representation of this bigger Clifford algebra. If you want to understand this in terms of configuration, what you have to do, before we have one lattice, but now I can draw the lattice like this, and I can label column in this letters by 0, 1, 2, and so on. And configuration is something like this. It is going on to 0 in this direction, but here, after some point, I have such kind of tail. And no big difference, it is more or less the same situation, and on such space, such kind of operators are acting, and so we have representation, and not only two, we can take many as we want. So this algebra has representation with such bases, and they can denote this representation by R, and then I can play the same story. Not big difference. So I can write down, for example, psi1 z t. It is the sum of psi1 I t minus I, and similarly I can write down these, and I can write down a dual first of all, here when I write, I forget to put star here. In a Clifford algebra, this with this, it is our previous situation. And this with this, it is also our previous situation. And here, 2 is here. So it is just, yes, excuse me, I wrote this incorrect. Anyway, I have this and this, and I have psi star 1 t and psi star 2 t similarly, and now in this bigger space I can do what? I can write, but well, it will be vertex operator algebra, so it means that correlation function of the product of such kind of operators, the matrix element will be rational function. Well, and important example of operators which I want. Let us write down EZ ET equal psi1 t times psi2 t. You know, they are acting in my space by the same way again. Psi are, now in my space I have 2 times of EI1 and EI2. And this is just product to such generators, and so I can do it. And it gives me some operators like this, and they are defined, well defined, because more or less of the same reason, even simpler than I discussed before. And they are acting in my space R, and I can ask about relation. And first of all, that E1t and E2t coefficients are skew symmetric, so they're Fermi. And from this, you can easily derive that Et1 and Et2 are commute. No, because if I write down such things, that the fact that this and this are skew commute, for product it says that they are just commute. So let us write down this. It is like this, without any plus. It is just usual bracket. And the other question that I can take this space and try to calculate Et1, Et2, and I can take some element W, say C1 here, W, say C2 here, into this, and I also expect, and it is easy to see, that this will be what? First of all, they commute. Therefore, it will be, what is this? It will be function in two variables, T1 and T2, which is symmetric. But not only that. I claim that for any W here and W here, this function M satisfies the condition that FTT will be 0 on the diagonal. And why? No, it is easy to prove by many ways, but I want to say that this is more or less evident because what? So I take element WC, and here I have psi1 T1 times psi2 T1, then I have psi1 T2, psi2 T2, and here we have other vector, so this is a real matrix element. But what we can say, that if we know that this is for fermions, this is skew-symmetric function, and because this is skew-symmetric function, it is 0. T1 equals to 2. And because this is also skew-symmetric function, it is also 0. T1 equal to 2. Therefore, our result will be symmetric function, which is 0 the diagonal. And this is what just I say. So it means that this symmetric function is has a structure. This is some G. Then it is T1 T2 times T1 minus T2 squared. Yes, and by the way, again, using some kind of notation with which I talked yesterday, it means the following: that well, in our space we have operators ET are acting, and again, the same story. It is, what is this? Coefficient EI, so this is summation of EI times T minus I. And then I look who is EI. EI, according to this formula, it is just the summation, the sum of psi I1 maybe alpha, psi 2 maybe beta, alpha plus beta equal I. Again, infinite sum, but it is acting on my space because of same reason to any vector. It is acting only final part of this formula is acting and non-trivial. And the condition that correlation function here is 0, this is some condition for that. And I claim that this condition, and just repeat, that the summation of EI, EG equal 0 if I plus G equal to some S. No, first of all, naively, it means that if you write down operator ET squared and write down this as the sum of EI T minus I squared, and write down coefficient here in front of some TS, then you get the expression of such sort. And I claim that this is 0. Yes. Well, now we can, using all this machinery, we can construct a little bit more interesting algebra. Yes, and this algebra has the following structure. In EZ we have ET we have, and this is psi 1 T times psi 2 T. And I also write down Ft. Ft is the same, but here I can use star. No, our construction is symmetric, and so it means that about F, we know that F no, let me write it by this way. F is psi I C minus I, and so Fi Fj is 0, and so just bracket it is the same as for E. What more than that? The summation of I of J, I plus J equal S is also 0. But our question, more interesting question about the relationship of E and F. Correlation functions can help us, at least to make calculations and also to find out the answer. No, this case is simple, and without any correlation function, you can take EI and Fi and calculate the break. But let me say something about this on correlation function language. So in my space I have vector W, C2, and then I can apply E T1 and then F T2. And then I have this vector, C1. And so what I can say about this? No, first of all, how to calculate. So this is psi 1 T1, psi 2 T2. And here is psi star 1, no, T1 is here, 1 T2, and here psi star 2 also T2. And so this is this, this is this. Yes. And then when I calculate matrix element, I can see non-trivial thing, pole here and pole here. And again, maybe it is better to calculation to make up more accurately, but at least it seems evident or at least reliable that such kind of function have a pole on a diagonal when T1 equal to T2, and the degree of this pole is equal to. So this correlation function is P, T1, T2, and here T1 minus T2 squared. Yes, and so this is easy to see from the fermions, but statement is that algebra generated by E T and F T, or better to say components, here is I and F G. E is isomorphic to the algebra SF2 hat on a level 1. And what does it mean? It means that no, it has to be some exercise, but exercise it means that I have this component and this component. And using correlation function definition or expression through fermions, I want to calculate just bracket, EI and FG, and just asking what is this. So maybe it can be a good exercise, or I can do it later. But my plan for today may be to make up a small break, 5 minutes, or a little bit more. And after that, no, because my lectures, the length of my lecture is not infinite. Therefore, I want to explain the little bit different things which I promised, some fusion type constructions, and then connected with this vertex operator construction which I am talking now. So this will be the goal of the maybe next hour. And no, but before do it, I want to say that in principle, if you understand how this machinery is working, we can do more things. For example, why not to take, no, let me only say this. So here I have indices 1 and 2, but I can, considering bigger fermionic Clifford algebra, the same, but adding indices 3. So suppose I have the object psi 1, psi 2, psi 3, for example, and psi 1 star, psi 2 star, and psi 3 star. Yes, and so three component Clifford algebra. Why not? And I can write down, for example, G T equal psi 1 T, psi 2 T, psi 3 T, and similar story maybe introduce Q is equal like this. Yes, and I can ask myself what kind of algebra is generated by these two things. And, no, first of all, such kind of algebra are this give us the special cases, what people are calling lattice vertex operator algebra. And if you ask about this specific case, then you see that in the previous construction I have a product of 2. Here I have a product of 3. No, because of product of 3, it means that G, if I write down here G I, G minus I, yes, then this Gi are skew commute, and the same for Q. So they are like a component of fermion, but they satisfy some additional relation. And this additional relation, we can get it more or less by the same way. So in this case, I can take W and write down here G T1, and so G T2, and here it is like this, and here it's like this. C2 and CP1. Again, I expect here some structure of this matrix element, and what it is. It is, first of all, it will build Laurent polynomial. And in this case, no poles, nothing. Poles appear if it is this with this. G with itself, not. And it is skew symmetric, but still no different psi with itself. But because there are 3, the corresponding things will have additional 0 on the diagonal. Because it is skew symmetric function, it means it is T1 minus T2 cubed times some symmetric function. So it means that such kind of G satisfies some extra relation and give us some interesting algebra. And even this interesting algebra I try to discuss a little bit next hour, but this kind of things from the point of relation to Gi, it means the following: the summation of Gi, Gj, and here we have I minus j here, I plus j equal s, it will be 0. And so it is a relation of such kind which such operator satisfies this relation. And in terms of generating function, it means that gt times gt derivative is 0. So this is just the same thing. And the similar story with Q. And what is possible to say? And this object is L.2 hat, and you can find this construction more or less in the arbitrary textbook about cut-smoothie algebras, because it is some construction of simplest. By this way, you get, in this case, it will be from other one point of view is some lattice vertex operator algebra, but in this case it gives us some superly algebra, and let me not explain this now, at least before the break, but I can say a name of this. It is the simplest possible representation of n equal to superalgebra. Yes, and no, if you want just to find what is this, you have no G is this, Q is this, but next calculation, just take G and Q and calculate the Q bracket of components, and just to find what is this. If you do it, you recover n equal to the superalgebra, and then you see that at least our possibility to construct algebra is even if we use only this machinery, we can construct very, very many of them. And even in this restricted mode, it's very interesting what we can get. Okay, let me make a small break.
They should take your mathematical, your question that. How many minutes?
Till 10, a little bit less.
Okay, well, less 10 minutes?
10 minutes.
10 minutes.
10 minutes, yes. How now it is understandable how this. For you, I understand, but not on concrete.
to do some calculation. That is most important. And so maybe better to make some calculation for this exercise. I will ask him how to calculate then he will.それで金曜日、私も明日から出られないので、金曜日やったら、金曜日終わったら、有沢さんに、山倉さんが渡してもらって、まあ、多分もうあんまり変わらないと。
Okay, maybe I continue. Yes. On. Okay. Anyway, I want at least to switch a little bit the subject, but just I return to this today. I hope, or in the beginning of tomorrow, lecture of tomorrow. But what we have here, we have operators ET and FT, and vertex operator algebra technique. It means that I can form a lot of new operators that, no, first I can try to find ET square, for example, but it is 0. It is not the new things, it is just 0. I can write down ET times ET prime. I can try, but it is also 0 because it is derivative of this. Next these things I can try to understand what is this. But this is something new, and it is the object of my algebra, and I can involve with it some calculation, correlation function, and so on. And so I can continue this business and form many things, and no, this E with E commutatives. So in the end, probably we understand all possibility to do it. But at least now we see that we have the object like this ET times FT, for example. And 2 dots mean that corresponding correlation function has pole, but we can take non-trivial. We can extract pole and forget about it and take next term and to do this. And it's also element of my algebra. And so this construction gives me this, and no, just I wanted to say what we have. Now, first, for some time, let us switch the subject, and I want to explain what is fusion procedure. Now, who heard the talk of Sergei Loktev? He explained something about this, and no, I want to understand what is this, and later the connection with construction of vertex operator algebra. But at least this construction is following. Well, suppose in the simplest case, suppose I have commutative algebra which generate by elements EI. No, let me change. EI was something different, so it will be AI maybe. I in my now is 0, 1, 2, 3, and so on. And now better the corresponding vector space labeled by this identify with just polynomials in T, and it is well, what I mean that I am talking about commutative algebra generated by EI. So this commutative algebra is polynomial algebra in infinite set of generators. The space of generators, for me, it is convenient to identify with other commutative algebra, just polynomial in one variable. But algebra itself is what I'm talking about. It is C, it is just something generated by constant, plus space of generators, it is T, plus symmetric power of this, it is Again, it is C, it is a space of generator V, this is symmetric power of V, and so on. It is space of polynomials. And sometimes it is convenient to identify symmetric power of polynomials in one variable just with symmetric polynomials in two variables. Later it will be important for me, but right now maybe not. It is just polynomial algebra of such kind. Well, or this is universal enveloping of the Lie algebra of commutative Lie algebra with infinite number of generators AI. Okay. Then what we can say about this Lie algebra, this notation, so Lie algebra, I denote, so this is universal enveloping, so this is universal enveloping of Lie algebra, and let me this Lie algebra denote by A, maybe it is Gothic A, it is this, and so now such kind of Lie algebra A, it has a so-called evaluation homomorphism to one-dimensional Lie algebra, and this is because it is Ct, then we can send T to some x and just value here, and it is going to one-dimensional algebra. Maybe it will be C sitting in a point x. Yes, and this is one-dimensional Lie algebra, and it has generator, and this generator maybe AX, something like that. It can be some notation. Well, therefore, we have conception of representation of Lie algebra. R that I will call it name sitting in a point x. What does it mean? It means that I can take one-dimensional algebra here, consider any representation of this one-dimensional algebra, and this homomorphism give me a representation of my algebra A. For example, I can take as a representation of Cx, n-dimensional representation, which is Cax over Cax times Ax power n. And so it gives me some representation of my algebra, and this all mean the following, that my representation, which may be good to denote Cn sitting in a point x, it has a basis with 0, v1, v2, and so vn minus 1. And because it has to be a representation of my algebra, then it means the generator of my algebra just function in Z. Yes, and representation, it means that each element from here, this element from here is just polynomial in Z. Yes, and action here is following. I have this polynomial evaluated in X. It is some number. And in a vector space with basis with 0, v1, v2, v3, it is acting by this way. Just from this to this is this product of X. This to this is also product of X, and so on. And who knows about the representation, evaluation, representation of affine the algebra? This is just it. Anyway, again, the construction is following. I take generator this, then evaluation in a point X give me map to one-dimensional representation, one-dimensional Lie algebra, and this Lie algebra is just polynomial in one variable, and generator is acting by one from this, and so on. And so it gives me the representation which I denote by, where I denoted by this. Well, if this is my construction, then what I can do. So I have my Lie algebra A, and then can construct representation C n1 x1 times C n2 x2, and so on times C ns xs. Also, tensor product. This is tensor product as tensor product of representation of abelian algebra. So, what is going on? We have collection of points, x2 and so on, xs, and over this, we have a representation of my algebra A, and so the result of this construction, we have representation depending on a point x1, so on xs. No, by our construction, no, in principle, it is not, in our construction, it is not necessary to for the point x1, xs be different, but for me it will be important, because the representation which I have here, no, it is simple representation of commutative Lie algebra, and it is some property of this representation is evident, that this representation is cyclic. And I want, no, the idea of a fusion is make some procedure when this point x1, x2, no, this is true if point x1 and so x are different. The idea of a fusion try to define the cyclic representation which are when point x1, x2, and xs are coincide, for example. And how to do it? So my representation, this one, is cyclic. So it means, no, the fact that it is cyclic, this is simple exercise. Each of, when x are different, each of them is cyclic, and then you can easily check it. And so it means that this representation, this one, because it is cyclic, this is universal enveloping of my commutative universal enveloping of this Lie algebra. And I can factor, because this is a representation and it has cyclic vector. And cyclic vector is what, by the way? Representation is this n-dimensional representation. I said it is V0, V1, and so on, Vn, and 1 minus 1. It is here. Here the same, and so on. And so this has cyclic vector which with 0 depending in x1. And in this tensor product we have vector like this with 0 x2 times so on, and so it is with 0 xs. And I said that this is cyclic vector, but more precisely, cyclic vector is this. And no, it's natural choice of cyclic vector, and so it is it. And so, because it is cyclic vector, I can apply universal enveloping to this cyclic vector, and the representation is the quotient of universal enveloping by some ideal which consists from the element of my universal enveloping which kill this cyclic vector. And so surely this ideal depends in x1, x2, and so on, xs. And surely in choice of representation, it depends in n1, n2, and so on, and ns. Yes. So if we define fusion by rather abstract way, we just can say, well, I take, so I have S-dimensional space, and x1, x2, and so on, xs is some point here. And suppose I am interested in a point 0, 0, 0, 0. Then I, on vector space of parameters, I can choose some way when this x1, x2, and so on, x1 is there depending in parameter on this line, and it is going to 0. Yes, and so if I make this, then now this family of ideal depending in T, and because it is one parameter family of ideal, it has some limit. And so I can take such limit and taking a quotient and just say that the result, the fusion is this. Now, this definition is nice, but first it is completely non-evident that the result does not depend on the choice how we go to 0. In principle, we can have many ways to define the fusion and many fusions. And usually it is not simple theorem that, for example, in this case, result does not depend how we go to 0. So the limit of the family of ideals when all x's are go to 0, it is 1 point. If you change the situation a little bit, that it is not change the situation, it means if you take different representation, different A, and so on, but at least in this case it is true. And let me say a slightly different way to define the representation, and let me do it's very similar construction, but slightly different. So I have some again, I have representation of my universal algebra of A depending in parameters x1, x2, and so on, xs. And it has, let me take this product of vectors. This is in my, so I have representation maybe denoted by rep, and about this representation, I know that in this representation, this is cyclic. And some vector may be denoted by W. It is this. It is cyclic vector. So Lie algebra A, no, it is can be then by definition. It is Cx and it has basis E0, E1, E2, and so on, and it is 1, it is x, it is x squared, and so on. And Lie algebra A is graded. No, grading is just this, grading of the grading of EI is equal I. But our representation, which in this case, it is not graded. R is not graded. But let us make from R the graded representation by force, by hands. And so how? So R is not graded representation, but at least it generated by W. And this algebra is graded, so universal enveloping of A is graded algebra. So universal enveloping of A is graded commutative associative algebra. It is C plus, it is something grading 1, it is something of grading 2, and so on. Anyway, so and this is grading 0. And surely in grading 1, we have only one element E1. In grading 2, what we have? No, not only that, we have, yes, it is not correct that E0 have grading 1. So therefore, here, no, it is wrong. And So this part is C is 0. It is grading 1. This part is C is 0 times E1. And so on. And here, what we have, C is 0 times E1 square or E2, and so on. But anyway, it is some graded space. And after that, in such construction, what I'm doing, I take my representation R and consider here on representation R is the filtration. What is the filtration? That first term is this grading 0 times W. Next term is no, my 0 is here. So here I just take this part and apply it to highest weight vector. Then I take this plus this and apply it to highest weight vector. It is bigger space. So it means in our case that I have what I have here plus and I apply to this. Next, I have a part here and apply so on, and as a result, what is this? Will be R0. This part is R1. Next is R2, and so on, and it gives me this. And it will be just filtration on my representation. For construction of this, I used only the fact that my representation is cyclic, and algebra has grading, nothing more than that. And next, I can considering the corresponding adjoint space to this filtration. I can take R0 plus R1 over R0 plus R2 over R1 and so on, and it gives me the space R, let us call it adjoint, and now it will be graded representation of my commutative algebra. Yes, so what is going on now? I have two different ways of operating, but these two different ways actually are not completely different, and if you try to compare it, you can easily find that they are not. Well, but again, non-trivial theorem, even in this case, that if I collapse point axis to one point, or by force make a representation graded, the result will be completely the same. It gives me some representation of some graded representation of commutative algebra. One point I collapse and ideal is going on to 0, it is even not evident that the result will be graded. Actually, it can be not, but in this case, it will be the same. Well, so let me consider the example. Suppose No, again, technically, if you want to calculate how this kind of procedure is working, my second procedure is, no, it's just more concrete. You are doing some concrete things and can calculate. If you just send x's to both or all of them to 0, then you can do it by some way, but real calculation is more complicated. How to calculate what it will be in a limit, it is not so easy. But about example is following. So suppose we take 2 points, x1 and x2, and 1 equal to and 2 equal 2. So what does it mean? I have a abelian algebra. In x1 is sitting 2-dimensional representation. In x2 is sitting is also 2-dimensional representation. And then I take tensor product of this 2-dimensional representation, and it will be something 4-dimensional. And then I wanted to make up my graded procedure. And this graded procedure, how it works. So you see, you have the tensor product of 2 highest weight vectors. Then it is W, or then I apply E0 to this, and if I apply E0, how E0 is acting? Here and here. So it gives me linear combination of product this times this and this times this. If I apply it again, it gives me a product of this and this. So it means that in such choice of R, R0 is a 3-dimensional subspace, and all space is 4-dimensional. Therefore, R0, the result of my adjoint space is what? I have 3-dimensional space plus 1-dimensional space. And it is 3-dimensional. It is natural to write down it by this way. And then, no, because this is adjoint things, then we can see how operator E0 is acting. E0 is acting by this way. And to this vector, it is acting by 0 also. Then we can look how on this, in A, we have also A1. And this A1 is acting actually by this way. And it is acting by 0 to this vector and acting by 0 to this vector. And as a result, you have C2 times C2 as a starting point, and as a result, you get something like this. And what this construction is given to us, that, no, we'll take a little bit more carefully later, but this is just 4-dimensional space. But here it is also 4-dimensional space, but it has grading. It is 0 and this is 1. And because now it is grading, it has Q dimension. And this Q dimension, we count this as 3. And this is 1-dimensional plus Q. And yes, and so this is a result of such kind of activity. If you take, for example, C2 times C2 times C2, which is sitting in the points x1, x2, and x3. So what is going on? So this space is 8-dimensional, but by this construction, you get on this space some filtration and also some action of these operators EI. Well, and the situation is similar because, again, we take highest weight vector and acting by 0, and now this 3 become 4. And it will be R0. No, I cannot make up full calculation even in this simple case, but I want to say that in this case the situation will be like this. So it means that R1 is bigger by 2, and R2 is bigger, and the corresponding, so you have this, and the corresponding action is following that E0 acting by this way. Yes, E1 is acting by this way, and E2 is acting by this way, and that's all. No more, only E0, E1, and E2 are acting here and give us such kind of a graded space, and yes, and the name of this construction in this case is graded fusion product. And then no, the relationship of this construction with our previous business, it is later, but the construction as itself, no, I want to say about this construction that it is very natural, but it is very complicated. Even in this case, it is not so complicated, but in more general situation, it is complicated to understand what will be the result. And let us just to discuss some kind of interesting examples where the answer is known, but before discussing, let me just formulate, surely not precisely, why this is how it is related with the beginning of my today lecture. No, the approximately not very precise statement, but what I can do, I can take C2 times C2 times C2 many times, namely n times, and then make up this fusion product. As a result, it gives me some vector space of dimension 2 power n. Next construction, so for any n, I get some vector space. Let me denote it maybe by Rn. Yes, and no, with some grading and with some action of this operator EI, and actually it has a richer structure. But now we have only a vector space with the action of EI, and it is also possible to organize the sequence of embeddings. How later, but the fact is that the limit of this can be identified with a part of my construction, and with what? I had before the construction of operator EZ and FZ, which appear as psi1, psi2, and psi1 star and psi2 star. What I can do after that? I can take highest weight vector because they are acting in some space, and consider subspace here when, no, I can take highest weight vector and acting by E and F and also combination to this vector. And so it gives me some subspace which is on other language is fundamental representation of algebra SL2 hat. And very remarkable and interesting fact that this kind of things can be realized as a limit of these spaces. Yes, and no, this is some phenomena which surely I cannot explain in full details, but it seems so interesting that it is reasonable to discuss this, because, well, it means that such kind of construction actually is some tool to construct some vertex operator algebras, and how actually this construction is going, it is not known. What is known that in some cases such kind of machinery is working, and usually the proof is you have vertex operator algebra and you can look to its representation and find there such kind of construction. Well, anyway, now this is I only claim that this is not completely separate subject, but related with what I'm talking about. But let me just discuss what kind of what kind of things we can do by this way. So my construction in this case was the following. I take abelian algebra, Lie abelian algebra, and this Lie abelian algebra, in my simple case, it is this. It was A, and I took the representation of this abelian algebra. For simplicity, better to take finite dimensional, but not necessary. Then I construct here the filtration. And then make up the adjoint things, and that's the question, what is this? No, in no, R, I took in very special special way. So I took the representation x1, x2, and so on, xn, and put some representation here, 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 and here, and then make up this filtration and get something. But I can do the following, for example. So, so here it was some other notation, maybe T. So how my construction actually is going? So I have universal enveloping of CT. Then here I have a map to polynomials in some generators. Maybe these generators let us denote by something, by B1, B2, and so on, Bn. And Natea map from this to this, it is following. That the generator from here, just function, is going to the sum fxi times bi. Now, this is rather evident way. So we have gomomorphism. So this is polynomial ring in infinite number of variables. This is polynomial ring in finite number of variables, b1, b2, and so on, bn. Yes, and before I applied my construction to a representation of this algebra, which is what? I take C, b1, b2, and so on, bn, and factorize it by ideal generated by b1 was maybe n1, b2 times n2. Maybe let us put n here, or there, I don't know, but anyway, bn times mn. And so this is the representation and what I considered, and then give us these things. But if look to my construction by this way, then in principle I can take here any ideal J here. If I want finite dimensional representation, the only condition that codimension of this ideal is finite dimensional, and then I can ask what is this. And in application, for example, this is let us take the following ideal, which is generated by the following things: b1 square, b1, b2, b2 square, b2, b3, bn minus 1, bn, and bn square. Such things or similar appear to in application, so I can factorize by this ideal, and then filtration, and so on. Maybe let me ask, just, no, because I close to the end of the lecture, and so here it is also explicit things. What is the dimension of the quotient? So before, when I take power of this, the dimension of a quotient was the product of numbers, and I get by this construction the Q version of a product. Now I'm playing a little bit different game, and so quotient is this, And so, no, and you see that this is this object is combinatorial. So what does it mean? It means that I have algebra which generate by B1, B2, B3, and so on, Bn, and I factorize it by relation. The square of this is 0, square of all of them is 0, and the product of these two, these two, these two, and these two is also 0. Yes, and I take this, and by this construct, it has some dimension. And no, by the way, not only dimension, no, it is also graded space, because at least it's just polynomial, this is homogeneous ideal. Therefore, at least it has some grading. And but by this construction, I get on this space extra grading by filtration and so on. But right now, just for the audience, simple question, what is the dimension of this space? You think so? But we take polynomial ring in B1, B2, B3, and so on, Bn. Factorized by ideal generated by these quadratic things. So how many elements survive after factorization? Now let us look. One survive. Yes, all B survive because it means we have n. Then in quadratic part is all products. It has dimensions n plus 1 over 2. But we do not like how we subtract from this how many elements? N, 2n minus 1. So it is minus 2n plus 1. It is like this. We factor out these elements. But then we take cubic things here and factorize up to consequence of these quadratic relations. And then we have something in degree 4 and also factorize and so on. And the question is how many. For example, if we have before, so B2 square, so B2, B3, B3 square, and so on. Before we considered the case where we did not have this. We had only B1 square, B2 square, and Bn square. In this case, after factorization, the dimension will be 2 power n. Because it is just all monomials. After factorization, we have all monomials where we never have a power 2. So just evident thing that number of such monomials is 2 power n. But now I add such things, and space becomes smaller. And what you can say about dimensions? No, and the question is in this case, this question does not relate it in my, no, it is related to my subject, but right now not. Because after factorization, I get monomials by I1, by I2, and by IM. After factorization, it means that we do not like power 2 because of this. And in the monomial, we have not elements bi plus 1. No. Then, but all other monomials survive, and then it means that we want to count how many monomials we have such that such condition is hold. That no, you can easily guess actually, but it is some numbers. If n is 1, no condition, it is 2. If no, because who is survive? 1 and b1. If no variables, it is 1. If like this, it is what? It is 1, b2, but product, it is 3. If it is 3, then how many survive? It is 1 plus 3 plus who is survive? This one only. So it is 5. Yes, and so it is standard question for mathematicians. Just continue the sequence. Mm-hmm. No, it's a Fibonacci number. Fibonacci. Catalan numbers we had here actually yesterday in a different problem. Here's Fibonacci numbers, and it is evident why, because if we go from n to n plus 1, it means what? In monomial, we can have this element or not. If not, this is situation here. If yes, it means that we cannot have square, and we have not have also this. Therefore, they are Fibonacci numbers. No, why I said this? So Fibonacci numbers, this is well-known things, and what is going on? And maybe this is almost the end. No, Fibonacci numbers you can understand, for example, by the following. If you draw the Pascal triangle like this, then Fibonacci number, for example, this 5, no, it is sum this, and this. 1, 3 plus 1. No, it is what we had here. Because here we had polynomial of degree 0, it is 1. B1, B2, B3, we have 3. And degree 2 is this, we have 1. And they are binomial numbers, and then are like this. And if it was 2, then it was 1 plus 2. And if you go to the next 8, it was 1, 4, 3. And but now, so anyway, it is Fibonacci numbers, but my construction with fusion gives you additional grading on this space. And especially also additional grading on this 1, 4, and 3. And so it has to be not binomials, but some Q binomials, some polynomials depending in Q. And in this case, they will be some version of Q binomial coefficients. So by some version that we have, no, binomial Q binomial coefficient, there are at least two different definitions, but they're depending by power of Q in front. And this, they will be some Q binomials with some Q power in front of them. And this I want to illustrate how in this a little bit non-standard and case, this fusion construction is working. It means that we have some combinatorial things. No, you see what is going on. We can understand the situation by the following. If you define Fibonacci numbers, what you are doing? You consider, you take n points and consider configuration of points. It's monomial in my case that no crosses can be in the neighborhood positions. Then what, so such kind of combinatorial problem, no, you can count how many things you can, and in this case it is Fibonacci numbers. But this construction, ideologically means the following. Then you put x1, x2, x3, and x4. This point you understand not just a point, but a point of a line. And then you send all these points on a line to 1, to 0. And what before they collapsing what some combinatorial data in a limit, it gives me some graded story. And this graded story is a fusion. And this is just what I am discussing. So this is the procedure. Well, and just to end my lecture, no, this construction is very, it is simple, and so it deserves to study, but not many things is known about how it is working. No, I cannot explain surely the details, but tomorrow I explain at least what in this operator algebra would coincide with the result of such kind of construction in a simple example, and maybe it is interesting by itself. Okay, let's